Welcome back to the Algebra 2 series. Today we're looking at the ellipse, and this is the third of our four conic sections. We've seen the circle, and we've seen the parabola, and now we move on to the third one, the ellipse. The definition here: in a plane, the set of points such that the sum of the distances to two fixed points is constant. And this is the key word here, constant. And as you can see at the bottom of the screen here, I've got a yellow line that is representing that constant sum. In other words, if you pick a point and you anticipate that that point would be on the ellipse, then the distance from the first fixed point to that point would be d1, and the distance from the point to the other fixed point would be d2, and d1 plus d2 in all cases should equal that yellow line. And that's the idea here, is that we're trying to figure out all the points in the plane that would be in that location so that those exact conditions would apply. So in order to see that a little more clearly, I'm going to move to this animation. Notice here in the Wolfram website that the red line, you see the two distances added together, and those two red lines, no matter where they are, will add to the same distance. And that's the tracing of what you get with the ellipse. So let me show you a little more about that. There are four very special places. The first special place is if we were to consider a point out here somewhere, the distance from the first fixed point out to here would have to be retraced back to the second one. In other words, we're going to move from the first fixed point all the way out to the side and then back to the second. Now the same thing's going to happen if you move to the left from the right side one. You go all the way out here and then back to here. So notice that this part has been counted twice. Well, one of the things that we can do then is we can say, let me put my two dots back in there, my two fixed points. We can see by moving this yellow line up that indeed that would be the position right out here. If we move from here straight out to there, and then we have to go back to here, this length over here would fill in that other spot. Now, what that does for us is it shows us what some values could be. So there must be a point out here that's on the ellipse. There must be another point over here. There are two more points, and those can be found if you simply take the yellow line and cut it in half. And I'll try to estimate that about here. And from my two fixed points, we're going to go up to the top and back down, where I cut in half. This line goes here, this line goes over here, and now we've got another point, one at the top there for, let me just move this stuff off of here so I clear this up a little bit. So there's a point at the top that would be on our ellipse, and there's a point directly below that as well. I'll move this guy, oops, I'm making a mess here. I'm going to move this out of the way a bit, and I'll put another point down here somewhere. Now, of course, I'm trying to draw this by hand, what you saw that very nice animation of just a moment ago, but this is basically what you end up with, is a neat little picture right there. And of course, the center is right in between. Now, the neat thing about this is that that yellow line comes right in here in the middle, and that becomes the major axis. Let me write that down here. This right here is the major axis. And if we were to explore this one, this would be the minor axis. And we have three different lengths to be concerned about. Obviously, we have the center, so we'll call that C. This is a focus. This is a focus. Foci is plural, so FOCI is the plural of focus. And then we have vertices out here. And the vertices in the ellipse, you have two of them. Finally, at the top and bottom, these are endpoints of the minor axis. I call those EMAs, endpoint of the minor axis. And let's fill in the rest of this. The last thing we need to put in here is the fact that we tend to locate this length from center to foci as little c. I remember that because foci has a c in it. And then the distance out here is to the vertex is a. And I remember that that is an A because it's part of the major axis. There's an A in major. Oh, that's sweet. And then the last one over here is this one, and that's a B. And I remember that that is the endpoint of the minor axis uh, because it's not one of the other ones. And that's about all I can do for that. So we have an A, a B, and a C. A, B, and C here. C is, it looks like less than A, and of course A is greater than B. And if you take a look at this relationship, I'm making a bit of a mess of my picture, but if you look at this relationship right here, you see that there's a right triangle formed, and this A value is also the length of that A, that hypotenuse. So we'll see that in our computations. Let's move on to an example and take a look at a few of these in their algebraic form. Starting with this part, there's a horizontal one, and this is a horizontal with center HK. Now a good example of that might be, for example, if I had an x minus 1 squared and put that over 16, and then I had a y plus 1 squared and put that over something like 9 equals 1. That tells me a few things. The h and the k stand for our center, and this is a squared. So that's going to tell me how long the longer part of the ellipse is, and this is representing b squared. That's going to tell me the length of the minor axis if I work that out. So let me just put this in here. The center is going to be at 1, negative 1. That's coming from the positive 1 here, and then that's going to be a negative 1 there. And the a value is going to be 4, while the b value is 3. Remember, I have to take the square root of those values in order to get the actual numbers. So a is 4, b is 3. Let's graph this and see what we get as a picture. So let's see a C, a center being 1, negative 1. And then since a is 4, that means I'm going to be going in the horizontal direction because it's underneath the x. I'll be going 4 units to the right and the left. So 1, 2, 3, 4 to the right, and 1, 2, 3, 4 to the left. So I'll put that in there and there. Those 2 points represent my vertices. If I go up and down 3 units, that will be an endpoint of the minor axis. Move this down just a bit. 1, 2, and 3. Endpoint of the minor axis, so another EMA. All right, so we've got our nice looking points there with the center in the middle, and then we'll just graph that. Not perfect, but, you know, sketched by hand. We've got our nice thing here. Here's the major axis coming across here. Now the only other thing we're missing, we've got the center, is we're missing where our 2 foci are actually located. We know that they're located somewhere in this area, but we would like a little bit more specificity here. So in this case, there is a Pythagorean identity that says a squared equals b squared plus c squared. And you might wonder, where is that coming from? Well, it's actually coming from the last page. Let's go back one more time here. And remember, in this triangle, this a value is like the hypotenuse of that triangle. And so because of that, we see that a is here, b is along here, and c is along the bottom. So that gives us the a squared equaling b squared plus c squared. Not quite the Pythagorean theorem that we remember, but it does give us a nice way to solve for the c value. So in this case, I would get 16 is equal to 9 plus c squared, or 7 equals c squared. So c is equal to radical 7. Now, of course, that's a plus or minus just to show us that we're going to move right and left radical 7 units, which is maybe a little farther. I have it pictured a little farther than it should be. Radical 7 should be between 2 and 3, so about here perhaps would be our focus. And maybe a little bit closer in, yeah? All right. Finishing out this video, I want to do one more here, and so let's take a look at the vertical ellipse with the center at HK. And notice the only thing that has changed between the two is that the a squared has moved over to be underneath the y. So in other words, we have a greater pull in the vertical direction than we do in the horizontal direction. So as an example for this one, we might have x plus 2 quantity squared over something like 4, and then a y minus 2 squared over, say, just something like 8. And that tells me then that if 8 is equal to a squared, then a is 2 radical 2. And if b is equal to 4, then I'm sorry, excuse me, b squared is equal to 4, then b is equal to 2. So we know then that we can graph this based on that information. Let's work this out. In this case, the center is going to be at negative 2 for the x and positive 2 for the y. That goes out here in quadrant 2. In order to graph the vertices, this time I'm going to go up and down a units. So that's approximately, not quite 3, maybe a little less than 3. We'll go up about 2 3/4 there, and then down 2 3/4, about here. And left and right 2 units. So that would give me the horizontal side. I'll just draw this picture in here, and we end up with, mine looks a little bit like an egg, but that's okay. Here's my center. Here are my vertices up and down. Here are my endpoints of the minor axis, endpoint of the minor axis. And we could calculate c in this case because a squared is equal to b squared plus c squared. Or in our case here, 8 is equal to 4 plus c squared. As it turns out, c squared is equal to 4, and therefore c is equal to plus or minus 2, which happens to be the same as the b value, except that the c value is going up and down. So notice here, we're going to go up and down 2 units with a focus here and the other focus up there. So these are a little tricky to find, but you're going to notice that we'll do this quite a bit throughout this section, finding those vertices, the foci, and the endpoints of the minor axis. I'll continue this in video number 2 right after this.